So now we will talk about the entanglement. Okay, quantum entanglement. This phenomena rather is significantly used in quantum computing. So we need a little bit of background, and which essentially is quantum mechanics. That's something that we need to learn before we learn quantum computing in detail. So here we will learn about something known as the EPR paradox. EPR stands for Einstein, Podolsky and Rosen. So this stands for Einstein, Podolsky and Rosen paradox. So this is well known in the popular physics world that Einstein was kind of suspicious of the probabilities inherent in quantum mechanics. So there was those famous, the Bohr-Einstein debate. So he tried unsuccessfully, of course, to pinpoint an intrinsic contradiction in the quantum theory. And then this theory went ahead, and the debate went ahead, and in the climax, he formulated this paradox. So what is that? Now imagine we have an elementary particle, right? An elementary particle with zero charge. Okay, so this is a particle which has zero charge. You can consider it as a neutral pion. Okay, we represent neutral pion with this sign. Now this particle is at rest. Okay, but this is not a very stable particle, so it disintegrates into an electron and a positron, and both of these, electron and positron, are fermions, and they have spin half. Okay, so this disintegrates into an electron and a positron, and both of these has spin half. Now angular momentum is conserved in this decay, so the two spin half particles, okay, they must together combine to form a spin zero state. So this pion, neutral pion, has a zero charge and a zero spin. So conservation of angular momentum demands that both these particles that gets created, their spin should be oppositely directed. So if we measure the electron spin to be up, right, then we know that the positron spin must be down, and vice versa. So there is no problem in there. Okay, so electron and positron are separating rapidly in opposite directions, and this again is the conservation of linear momentum. Now if we make the first spin measurement on the electron then we can say that in principle we can measure the positron spin before even a light signal had time to communicate between these two particles. Okay, when we say that the light photon to communicate between these two particles, we really mean that even for light there is no way that this communication can go from electron to positron that we have measured the electron. Okay, and we have measured the electron to be having a spin half. All right, so no matter what we do, we will always find a perfect anticorrelation. A perfect anticorrelation between the particles, or rather say, since we are measuring a quantum entity, between the spins. Okay, even though there could could have been no physical communication between the two particles. Okay, so now Einstein thought that this demonstration, so this is a thought experiment, okay, and Einstein stated that this demonstrated that the spins of these two particles, right, are determinate. Before measurement. So even before we measure, the spin is actually half, and this spin of the positron is actually half on the opposite direction. So it was determinate. That's what Einstein's idea was. So these are actually, when it is determinate, we say that these are actually the elements of physical reality. So this version was of Einstein. Okay. Now we know that we had Bohr's Copenhagen interpretation. And there he says that it is really meaningless to talk about the spin direction of the particles before we make a measurement. So until and unless you do not make a measurement, we cannot really talk about a spin direction of a particle. Okay, this is a truly the weird thing that we say about the quantum mechanics. So basically this means that there is no objective reality. Now these are the physical terms that we associate with quantum mechanics. So according to Bohr's interpretation, there is no objective reality. So that essentially means that a quantum mechanical phenomenon is a reality. If we say a quantum mechanical phenomenon is a reality, so it's a quantum mechanical reality. This reality is really independent of an observer. Okay, so for electrons and their spins and all, so until we measure, we do not know, we cannot say what is the spin of the particle could be. Now Einstein thought that these things must really be predetermined in advance of the measurement. So present formulation of quantum mechanics has this spin. Now we know that it has only probabilistic value. So this faster than light communication is really doesn't mean anything. It's out of the question. So what could happen? So there must be some hidden variables. There must be some hidden variables that is actually responsible for the decision of these spins. If this is half, this is minus half. Okay, and this hidden variable, the quantum mechanics doesn't have any knowledge about. So there had been frantic activity for several months to form a response to Einstein's challenge, and then Bohr declared that this EPR paradox is not really a paradox. This was according to Bohr. Not really a paradox, and he then argued that quantum mechanics demands that you are only you should treat, quantum mechanics demand you should treat this electron-positron system, electron-positron system as a single quantum system. Right? Then there the matter somewhat rested. It remained a kind of abstract and philosophical debate about hidden variables and objective reality, and so neither side denied that quantum mechanics worked as a predictive framework. Okay, so both of them were kind of unanimous that quantum mechanics is really a predictive framework. There was no denial from either side. Now then came John Bell. So he then tried to put, devised a way to how to unite these two views, like hidden variables versus objective reality. Or rather, this hidden variables objective reality, not versus line. Hidden variables objective reality, that was one view. And quantum mechanics, and no objective reality. Now, how how can we transcend this philosophical debate to something which is physics? And when we say physics, we actually mean that a theory should have an experimental test. So here we discussed that measuring spin in up and down direction. What happens if we measure the up-down direction for electron and left-right direction for positron? So basically, what I mean is that we determine for electron, we measure up and down. So for electron, we measure up and down, and for positron, we measure left and right. Now, with quantum mechanics, this is very easy to calculate. Okay, we will, in our later lectures, we will actually visit these things in pretty detail, and not in this very small introduction. So basically, if we find that the electron is in the up position, the positron state must be down, and by standard quantum mechanics, a down state may be written as an equal superposition of left and right eigenstates. Superposition of left and right. So, when we measure, okay, we measure the left and right kind of measurement on the positron. Okay, that would yield right or left with equal probabilities. Okay, so 50% of the time I will get the positron having a spin left, and 50% of the time I will get a positron having spin right. Okay, so John Bell, what he did, he considered the correlations. the correlations predicted for spin measurements, not at right angles, but at an angle of, say, 37 degrees. So this is very important to understand what John Bell did, that he considered the correlations predicted for spin measurements, not at right angles, but at an angle theta, say 37 degrees. Okay, so in this case, the probabilities for up and down, so with this new direction, so up and down, when we measure about at an angle 37 degrees. Okay. Right, 37 degrees. These are not equal. Had it been a 45 degree, it would have been equal. But 37 degree, it is not equal. These are unequal probabilities. Okay, not equal and not purely random. So in this case, the probabilities for this up or down, right, in these new directions at an angle theta are now not equal here they were equal, 50% probability. Here they are not equal. So basically, say for example, the up has a probability n and the down has a probability of n. So n plus n is 1, of course, but this n is not equal to n. So these are not equal and they are not purely random. And then Bell proved that the correlations predicted by quantum mechanics are greater than could be obtained from any local hidden variable theory. Now, you will not understand this in its entirety in such a small span of our class, but the crux is this. So basically what he predicted, that these correlations here, he got correlations from quantum mechanics, he got correlations from, and he said that these correlations are greater than that could be obtained from any local hidden variable theory. Okay. Now, we are always saying that this local hidden variable theory, where we are referring to a term local pretty often. What this local actually means is local has an important significance in physics. This local means that there is no faster than light signaling. Okay. So there is no peculiar behavior, right? There is no any sort of acausal behavior. That's what local means. So there is nothing very peculiar happening. So this experiment, then what did it do? Very unfortunately for Einstein, and there were other co-workers like Alan Aspect and many others, this famous series of experiments, Alan Aspect and all, they demonstrated that Bell's hidden variable inequalities, so here I had certain inequalities known as Bell's inequality, these inequalities are violated. Had they not been violated, then the strength of the hidden variable theory would increase, but they has been violated. And that essentially means that nature obey quantum mechanics. So now this EPR state of electron and positron, so this of electron and positron pair. So we said that this is a single quantum system. Okay, so this state is really, we have a name for such a state. We call this state as an entangled state. We can, if you want to write it in terms of Dirac notation, we write it like this. We write this 1 by root 2. 1 by root 2 comes simply as part of a normalization procedure. It is just a coefficient, and this is the state that we write it like. So this is the state of the first particle, and this is the state of the second particle, and this is the state of the first particle, and this is the state of the second particle. So the first particle spin half, spin top, and the second particle spin down, and the first particle spin down, and the second particle spin up. Okay, so in EPR case, we have shown that these two electron-positron pair, these two particles, are rapidly flying apart. Right? So these two particles rapidly flying apart means these two particles are distinctly two different entities. But what we see in the entangled state representation of these two particle quantum system is a very unique thing. that it is not possible to write such a state as a simple product state of particle 1 and particle 2. It is not possible to write it at all in such a form. So particle 1 is not in a definite spin state. The spin information is rather, so this is something important for us to remember, that the spin information is shared between the two particles. Okay. So if we consider this in terms of quantum computing, instead of two particles, if we talk about two qubits, and say we represent this 1 by root 2, the spin up of a state, we represent it as, say for example, spin 0, and spin down as spin 1, as spin down 1, and this is 0 for particle 2. We then call these two qubit as entangled qubits. Okay, so, and it is possible to show, later on you will see, we will work with these entangled qubits too much in quantum computing. This can be more than 2 qubits as well in a multi-qubit system. So it is possible to entangle 3 qubit, 4 qubit, 5 qubit, 6 qubit, and as we go along, the power of parallelism increases. Okay, so with such states, the quantum mechanics shows non-local power. As we said earlier, that local means nothing weird, no faster than light signaling, no peculiar behavior, no acausal behavior. Non-local, we exactly mean the opposite. So how do we entangle states in quantum computing? So we have seen how we define these gates in quantum computing before. So let us try to remember that the quantum CN, or controlled NOT gate. Okay, so how it worked, it's a qubit 1 and qubit 2. These are their timeline. Some point of their timeline, we write a controlled NOT gate. We apply a controlled NOT gate. So this remained as Q1, and this became the XOR of Q2, Q1 and Q2. Okay. Now, if we apply this transformation to a product state, okay, then we generate precisely a state of this EPR form. So basically we say that this one is what it is. It is UCN. It is 1 by root 2 0 plus 1. What happens if we apply it to a 0? So this will become, we can write it like this. This becomes 0 0 plus 1 1. So it is sharing the first two halves of the entangled pair. That makes possible such things we will see later on, that we call it the quantum teleportation. Quantum teleportation. So interacting with one half of this EPR pair affects the other half in a non-local way. So this is a very essential ingredient of, you will find this in almost all quantum algorithms. On quantum computer.